In this project, we'll find the shortest path from the rabbit to the turtle if we can only move straight to the right or left and straight up or down. To find the shortest path, we'll use something called Dijkstra's algorithm or recipe. I've taken this project from a very nice one done by Adam Halo. The link to his project is in my project notes. Let's begin. You can see that I start with 3 lists: a distance list, a previous cell list, and something called the stack. As the project unfolds, you'll see how the lists get used. The lists have been set up with starting values. The position of the rabbit in cell 1 is marked with a 0. There are 8 other cells named 2 through 9. They are here: 2, 3, 4, 5, 6, 7, 8, and 9. Some of them are underneath these tables or lists. All of those other cells are marked with the number 999. Dijkstra's algorithm knows that the turtle is in cell 5, but it doesn't mark the table at this time. The previous cell list is set up with -1 in all cells, and the stack is empty. I start by exploring the area around the rabbit. The rabbit is in cell 1. We can also say the rabbit is in column 1 and row 1. We're going to look at all the adjacent cells to the rabbit that are on the game board. So we're going to look here at cell 2 and here at cell 4. Remember that we don't move diagonally. We're going to move east and examine cell 2. Now I look in my distance table and I ask whether the number in the second row of the distance table is greater than 1. Why 1? Because I've moved just 1 cell to get here. And it's true that the number here, which is 999, is greater than 1. Now I look at another value in the distance table. It's the value at 5. Why 5? Because the turtle is in 5. 1, 2, 3, 4, 5. And I see that that number is also greater than 1. So it means the cell I'm examining, cell 2, is on the shortest path. I've traveled 1 cell from the start. I'm going to update the distance table for cell 2 to show a distance of 1. Now the previous cell, the cell from which I came here, was cell 1. I'm going to put cell 1 in my previous cell table right here on line 2. Now we're going to explore cell 4. Remember that we're still exploring the cells around the rabbit. Again, I'm going to look at my distance table for the cell I'm exploring and ask if it's greater than 1. And it is. 999 is greater than 1. Then I'm going to look at the distance table for the turtle cell, and I'm going to ask whether it's greater than 1. And it is. 999 is greater than 1. So I answered yes to both questions, and that means that cell 4 is on the shortest path. I traveled 1 cell to get to 4, so I'm going to update the distance table right here to show that I traveled 1 cell. The cell that I came from to get here was cell 1, so I'm going to update the previous cell table right here to show a 1. Now, I've explored all the cells I can around the rabbit, and I'm going to capture what I did in these 4 letters, N, Y, Y, N. They're also down here in the stack. What do they mean? They show to the north, south, east, and west of the original rabbit whether this cell was on the shortest path. N means no, Y means yes. So this says to the north of the rabbit, we were not on the shortest path. To the east of the rabbit, we were on the shortest path. To the south of the rabbit, we were on the shortest path. And to the west of the rabbit, which would have been here, we were not on the shortest path. I made a little mistake in that explanation, so I'm going to go back again and say it's north, south, east, and west. To the north, we were not on the path. To the south, here, we were on the shortest path. To the east, here, we were on the shortest path. And to the west here, we were not. Now we can go on. I'm going to start a whole new search around cell 4. Why cell 4? Because this says to the south of the rabbit, we were on the shortest path. We need to explore around that cell now to see what our next step on the path will be. South of the rabbit is cell 4. As I did with the original rabbit, I'm going to start by moving to the east of cell 4. That puts me here on the turtle. And I ask myself, in the distance table, is the entry for this cell greater than 2? Why 2? Because I've traveled 2 cells to get here. And it is bigger than 2. 999 is bigger than 2. Now I'm going to ask myself whether the distance at the end point, that happens to be the same cell, is also bigger than 2, and it is. We've answered yes to both questions, so we know that this cell is on the shortest path. Notice that Dijkstra's algorithm does not know that we've reached the end point. Not yet. In summary, we traveled 2 cells to get here. So on the distance table right here, I'm going to put the number 2. To get here, we came from cell 4. So right here, I'm going to put 4. Now remember that we're still exploring the cells around 4. We just looked at this one. Now we're going to look at this one, north to cell 1. Again, I look at my distance table and I ask whether the entry for this cell is greater than the distance I traveled, 1, 2. And it is not. Then I look at the cell for the end point and I ask whether it's greater than 2. And it is not. It is equal to 2, but not greater than 2. So I answered no to those questions. And that means I don't have to do anything to remember information about cell 1 right now. So I've looked here, and you might be able to predict I'm going to look at cell 7 next. Again, I go to cell 7 in the distance table and I ask whether it's greater than the distance I've traveled to get here, greater than 2, and it is. Then I look at the cell for the end point and I say whether it's greater than 2, but it is not. So I answered no to one of those questions, and that means cell 7 is not anything I need to remember about now. In summary, only traveling to the east did I find a cell on the shortest path. So I put a Y for the east section, and then I go on. The Y in the east direction means that cell 5 was on the shortest path, and we need therefore to look at the cells around cell 5 to see if they're on a path as well. But as soon as we start to do that, Dijkstra's algorithm recognizes that 5 is also the end point, and it knows not to look any further. Then it simply deletes this entry and moves on. Now I'm starting a new search around cell 2. Why is that? Well, you might remember that the first time through, we put a Y here to show that east of the rabbit we were on the shortest path. So now we're exploring the cells around cell 2. We start by moving to the west, here. Now we've explored this cell several times before, but Dijkstra's algorithm does not know that. In the next steps, I'll use the distance I've traveled so far, which is 2. I traveled away from the rabbit to cell 2, and then back to the rabbit. Again, I go to the distance table for this cell, and I ask whether it's greater than 2. It is not. I then look at the distance table for the end point, and I ask whether it's greater than 2, and it is not. I answered no to both of those questions, so I don't have to remember anything about cell 1 right now. Remember that we're exploring cells around 2. I'm going to move here. I'm examining cell 3. I again look at the distance table for cell 3 and ask whether it's greater than 2, and it is. And I'm looking at 2 because I've traveled 2 cells to get here. Then I look at the distance table for the end point, which is here. I ask whether it's greater than 2, but it is not. I answered no to the second question, so I don't need to remember anything about cell 3 right now. I'm now moving south from cell 2 to cell 5. I look in the distance table for the cell I'm exploring, and I ask whether it's greater than 2. It is not. I then look at the same cell again, because it is the distance table entry for the endpoint. I find it is not greater than 2. So I've answered no to both those questions, and that means I don't need to remember anything about this cell right now. And then lo and behold, I've got all ends. It turned out that nothing adjacent to cell 2 was on the shortest path that I needed to remember about now. It turns out that I've explored everywhere I can according to Dijkstra's algorithm. That means I'm ready to show the shortest path. And the way I do that is I go to the end point and I highlight it. Then I look in the previous table to see where the previous cell was. It says cell 4. So I highlight cell 4. Then I look at the previous cell table for 4 and find that the previous cell was 1. And I highlight it. And I'm done.